Welcome to lesson 16 on power system analysis. In this lesson, we will talk about the power flow problem. In this lesson, we will start with an introduction to power flow problem. Then we will talk about how we formulate the Y-bus matrix. Then we will derive the power flow equations, and finally we will be talking about how we classify the bus bars into different types for power flow problem. Well, on completion of this lesson, you should be able to explain the significance of power flow problem, develop the Y-bus matrix for any power network, develop power flow equations for a power system, and classify different types of bus bars in a power network. Well, the power flow problem is one of the most fundamental problem in power systems. Till now we had discussed about the model for various components in a power system, and now we are starting with the analysis, and power flow analysis is the most fundamental analysis in power systems. Well, what we mean by this power flow analysis, which is also known as load flow analysis. Well, in a power system, what we have is, as you can see from this diagram, the load on the system keeps on varying all the time. That is, the load on the system is not constant, it keeps on changing all the time, as we had discussed earlier. And we have a number of generators which supply this load. Also, this load which we have shown here as a system load is not concentrated at one place, but it is dispersed at various locations. That is, at various substations we have loads connected to the system, and these substations are connected to the generators by means of a transmission and distribution network. Now, this power flow analysis, the basic idea here is to find out the voltages at different bus bars, that is the substations that we have, or the node points which we call, and the flow of power on these lines. So, that is the basic idea. Now, as we see from this diagram, the load keeps on changing, and this load is an aggregation of loads at various substations or bus bars. Therefore, we also know that the load at different bus bars are also changing. What we really do is we consider the loads at any given instant. That is, what we do, as shown from these lines, we consider the load at this particular instant to be this much, at this particular instant it is this much, and these instants that we choose are of very short duration. That is, if every 3 or 5 minutes, if we are choosing these load values, then we expect the change in load between two successive instances is not much, and for the time between these two instances or two successive instances, we consider that the load remains constant, and therefore, we can consider the network to be working in a steady state or a static operating condition. This kind of a classification of power system operating condition is called a quasi-static operating condition. That is, we are considering the power system loads and the power flowing on the transmission lines to be constant for a given instant and to remain constant for a short duration of time, that is the successive time instances at which we are considering. So, for this small period we consider the system to be operating on a constant load condition, and therefore, we can consider the system operation as a static operation, though the system as such will be changing its operating point from one instant to other instant. So, that is why we call this operating condition as a quasi static operating condition. So, in load flow analysis, what we do is we try to find out the voltages, the power flows and the power injections at various bus bars for any given operating condition. Therefore, load flow is basically a static network analysis problem for a power network. Now, let us start with a power network. When you see this diagram, it is showing a very small power network where we have considered 5 bus bars. These bus bars can be considered in actual system as substations. So, we have say a substation which we are calling here as bus bars. In power system terminology we call them as buses. So, this bus 1 is having a generator connected to it which is supplying say real power Pg1 and reactive power Qg1. Similarly, we have another substation or a bus 2 where we have a generator connected which is supplying power Pg2 and reactive power Qg2 to this bus. Bus 1 and 2 are connected by a line which we are calling line L1. Similarly, we have another substation or a bus 3 which has got a generator connected which is supplying real power Pg3 and reactive power Qg3. This also has a load of real power PL3 and reactive power QL3. It is also connected to bus 1 by a line L2. Similarly, we have other bus bars, bus bar 4 and bus bar 5. Here what we find is bus bar 4 is only having loads PL4 and QL4, that is the real power load PL4 and reactive power load QL4. Bus 5 similarly has only load real power PL5 and QL5. Therefore, we see that at some of the bus bars or the buses we have generators connected, and these bus bars we generally call as generating bus bars, whereas some bus bars have only loads connected to them. These we call them as load bus bars. We also have seen in this diagram that some of the generating bus bars like bus bar 2 and bus bar 3 have also loads connected to it. In fact, most of the generating bus bars will also have some load connected to it, because if you are running a thermal power station, then for your auxiliaries as well as for the substation supplying the local power for the residences in that substation in that power station, all these will have to be supplied, and these are the loads which will be connected to that bus bar. So, we in general have generating bus bar and load bus bars, and these are connected by means of transmission lines, transformers and other equipment, and thus these lines and transformers which are connecting these bus bars form the power network. And the whole idea of power flow analysis is to find out the voltages at various bus bars and the power flows in various lines, because we know that we must keep the voltage within a specified limit, as well as transmission lines have a capacity, and therefore, we must keep the power flowing on the line within its capacity. Otherwise, the line will get overloaded, and that may lead to other problems like protection system, sensing overload and tripping the line, etc. So, the idea for power flow analysis is to given these loads and generation to find out the voltages at various bus bars and the power flows in various lines, so that we can assess the operating condition of the system and see that none of the variables are beyond their operating range. Now, if we see any bus bar in detail, like if we say this bus bar 2, which we have put here, this bus bar, if we want to see it in detail, then we can see this as a generator is connected to this bus bar, which is injecting a real power Pgk and reactive power Qgk into this bus bar and it has a load which is drawing real power PLk from the bus bar and reactive power QLk from the bus bar. This bus bar is connected to other bus bars like bus I, bus j, this through this line to bus j and through this line to bus m. The voltage at this bus bar is Vk, where Vk is equal to the magnitude Vk and angle delta k for this bus bar. Now, one thing which we see from here, that this generator is injecting real and reactive power into the bus bar, whereas this load is drawing real and reactive power from this bus bar. What we can always do is we can take the algebraic sum of these two, that is, we can subtract this load from the generation, and that is the real load PLk from the generation Pgk. Then we can say that there is a real power injection into the bus which is equal to Pgk minus PLk. Similarly, we have a reactive power injection Qk which is equal to Qgk minus QLk. So, this can be shown as in this diagram, that is, we have now, instead of writing generation and loads at the bus bar, we are now talking about injection into the bus bar. So, if we have say a load bus, then there is no generation at that bus. So, what is going to be the injection? The injection at that bus is going to be, say for that bus Pk, if we look at that, then we have no generation, that is Pgk is 0, then Pk is equal to minus PLk, and similarly Qk will be equal to minus QLk. So, loads can be considered as negative injection, that is, the loads are drawing power out of the bus, whereas the injections we have considered to be positive when it is into a bus. So, if we see here, we have injections Pk and real power injection Pk and reactive power injection Qk, and we, as we have said, we are writing Pk is equal to Pgk minus PLk and Qk is equal to Qgk minus QLk. Now, we have three lines connected to this bus bar, one going to bus I, another going to bus j, and the third one going to bus m. Now, these lines will be carrying power Pki and Qki to bus I, Pkj, Qkj to bus j, and Pkm, Qkm to bus m. Now, some of these powers may be in the reverse direction, that is, they may be coming from say bus k to bus bus j to bus k. In that case, the value of Pkj and Qkj will be negative. So, we have here, let us say all these are the values of real and reactive power flowing on the line, then we can write that the real power injection into the bus will be equal to the algebraic sum of all the real powers flowing away from this bus through the transmission lines connected to this bus. That is, Pk will be equal to Pki plus Pkj plus Pkm. Same thing will hold good for the reactive power. So, reactive power injection Qk is equal to Qki plus Qkj plus Qkm. That is, what we are saying is that the real and reactive power injection at a bus is nothing but equal to the algebraic sum of the real and reactive power which is flowing into the bus, or negative of the real and reactive power, is equal to the algebraic sum of real and reactive power flowing out of the bus. This follows directly from the Kirchhoff's current law, that is, we cannot have any power or current stored here. So, whatever is the power or current flowing into the bus must go out from the bus through the transmission lines. Okay, so now we will start with power flow study, what we really are trying to do in this study. As we said, we are considering the power system operation as quasi static. Therefore, power flow study is basically a static network analysis for a power network. Then we have real power balance at all the bus bars and also for the total system, that is summation of all the generation, real power generation, minus summation of all the loads minus the loss in the transmission system is going to be equal to 0. That is, the power which real power which is injected by the generator has to be equal to the real power drawn by the load and the real power losses in the transmission line. Similarly, reactive power balance equation also holds good, that is, total reactive power generated by the generators or the transmission lines must be absorbed by the loads and the losses in the series element of the transmission lines. So, both real and reactive power balance equations hold good. We do this power flow study to find out the power flow on various transmission lines, so as to check that all the flows are within the limits or the carrying capacity of the transmission line. We also check for the voltages at all the bus bars or the substations, and to see that the voltage at all points are within a specified limit. Normally, this limit will be plus minus 5% or 10%, depending on whether we are talking about the high voltage system or we are talking at the consumer level or the low voltage region. Now, how do we do this power flow analysis, which is basically static analysis of the power network? What do we do here? First thing that we need to do is create a mathematical model for the network. For this purpose, as we had already seen when we developed the model for the transmission lines, all the transmission lines are represented by their nominal pi model. In fact, the very short lines can also be represented by just a series impedance, whereas long lines can be represented by an equivalent pi model that we had developed. So, a nominal pi or an equivalent pi can be used for medium line and long lines, whereas a simple series impedance can be used for a short line. We have also seen how we can model the transformer. Transformers are generally modeled by their leakage impedance only. We do not consider the magnetizing and the core loss part, because that is much smaller percentage of the current which is flowing or the power which is going into this shunt part or the magnetizing part, but also because the current in the two elements are almost 90° out of phase. So, the effect of this magnetizing part is not much. Now, we consider bus power injections rather than generation and loads separately. So, what we do is, we, as we saw just now, that we find out the injections at each bus bar, which we had seen is equal to the generation minus load at that bus bar. So, we can write the injection at any bus k as Sk. This is the complex power injection, which is Pk plus jQk, and we know this Pk plus jQk, or the complex power injection, is equal to Vk into Ik conjugate, where Vk is the voltage phasor at that bus and Ik is the current injection phasor at that bus. So, using this relationship, that is Sk is equal to Vk into Ik, we will formulate the equations for power flow. So, once we know this Pk and jQk and we know this Vk, then we can always find out Ik, that is the current injection into the bus, where Pk, as we had already seen, is the real power injection Pgk minus PLk, Qk is the reactive power injection Qgk minus QLk. Now, let us formulate the model for this power flow analysis. In formulating the mathematical model, we need to formulate first what we call as bus admittance matrix. We will see what this actually is. Now, I have taken here a small power system with 3 bus bars. The bus bar 1 is having a real power injection P1 and a reactive power injection Q1, whereas bus bar 2 has a real power injection P2, reactive power injection Q2, and bus bar 3 has real power injection P3, reactive power injection Q3. These buses are connected to each other through lines, like bus 1 is connected to 2 through line L1, 1 is connected to 3 by line L2, and bus 2 is connected to 3 by line L3. Now, if you model these lines L1, L2, and L3 by their pi equivalent model, then the circuit will look something like this, as shown here, where for a line L1 which is connecting bus 1 to bus 2, Y12 is representing the series admittance of the line, Y120 is representing the shunt admittance of the line, which is basically the line charging capacitance of the line, and at the end towards bus 1, similarly Y210 is the shunt admittance of the line at the bus end 2. So, this pi equivalent model is representing line L1, which is connecting bus 1 and 2. Similarly, we have the pi equivalent model for line 2 L2, which is connecting bus 1 and 3, and the series admittance is given by Y13. The shunt admittance part on the bus 1 side is Y130, and on bus 3 side is Y310, and so on. For line L3, we have the series admittance Y23, shunt admittance towards bus 2 is y230 and towards bus 3 is y320. Now, if we take these power injections and convert them into current injections, then having this circuit with us, we can now, using Kirchhoff's law, we can write the network equation for this system as shown now. So, if we do that, then we can write using the KCL that I1, the current which is injected here, will be equal to the current flowing through this branch, which will be equal to V1 into Y120, current flowing through this branch, which is equal to V1 minus V2 into Y12, current flowing through this branch, which is Y13 into V1 minus V3, current flowing through this branch, which is Y130 into V1. So, if we write this equation, we have I1 is equal to Y120 V1 plus Y12 into V1 minus V2 plus Y130 into V1 plus Y13 into V1 minus V3. Same way, we can write the equations for current injection at bus 2. I2 will be equal to Y210 into V2 plus Y12 into V2 minus V1 plus Y230 into V2 plus Y23 into V2 minus V3. Same way for I3, that is current injection at bus 3, that will be equal to Y310 into V3 plus Y13 V3 minus V1 plus Y320 into V3 plus Y23 into V3 minus V2. So, these three equations, which are relating the current injections I1, I2, I3 into the network with the voltage at the three bus bars, that is V1, V2 and V3, can be arranged in a matrix form as I1, I2, I3 is equal to, here in this matrix we have Y120 plus Y12 plus Y130 plus Y13 into V1. So, we have this element minus Y12 minus Y13. Similarly, here we will have minus Y21 into V1 plus Y210 plus Y12 plus Y230 plus Y23 into V2 minus Y23 into V3 for I2, and similarly for I3 we have minus Y31 into V1 minus Y32 into V2 plus Y310 plus Y13 plus Y320 plus Y23 into V3. So, this equation can be arranged in this fashion in a matrix form, and this we can write as I1, I2, I3 is equal to capital Y, we are writing here Y11, Y12, Y13, Y21, Y22, Y23, Y31, Y32 and Y33, V1, V2, V3, where Y11, the diagonal element, is Y120 plus Y12 plus Y130 plus Y13, and the diagonal element Y22 is Y210 plus Y12 plus Y230 plus Y23. Similarly, diagonal element Y33 is equal to Y310 plus Y13 plus Y320 plus Y23. This is what we get from the matrix that we had seen here. So, we are replacing this element by Y11, this element by capital Y12, this element by capital Y13. So, we can see that the other off diagonal elements Y12 is equal to Y21, and that is equal to minus small y12, that is the series admittance of the line between 1 and 2, it is negative of that, and y13 is equal to y31 is equal to minus y13, y23 is equal to y32 is equal to minus y23. Now, this matrix sorry, this matrix y matrix of y admittance elements is relating the current injection at the various bus bars to the voltages at the bus bars, and that is why this matrix y matrix is called the bus admittance matrix. It relates the current injections at the bus bars to the voltages at the bus bars. Now, the elements of this y bus matrix YII, that is the diagonal elements, is called the self admittance or the driving point admittance of the network at bus I, and the element Yij, that is the off diagonal element, is called the transfer admittance or the mutual admittance between bus I and j, and in short we can write this relationship as I bus is equal to y bus into V bus. We can in the same way write this relationship also as V bus is equal to Z bus into I bus, where Z bus is the inverse of Y bus matrix, and Z bus matrix is called the bus impedance matrix. Now, we normally work with the bus admittance matrix and not with the bus impedance matrix. There are various reasons behind this. One of the reason is it is very easy to form the Y bus matrix by just inspecting the power network, whereas Z bus matrix is much more complex to form. The other aspect which is there is that Y bus matrix is generally sparse, whereas Z bus matrix is a full matrix. We will see these things. So, let us see what are the characteristics of this Y bus matrix. The dimension of this Y bus matrix is n into n, where n is the number of bus bars in the system. So, if you have a 3 bus bar system, as we had seen here, as we had seen here, we had a 3 bus bar system. For this 3 bus bar system, we will get a 3 by 3 Y bus matrix. If we have a 10 bus bar system, we will get a 10 by 10 matrix. Normally, the power networks are very large, they are more than 1000 bus bars with many thousand lines connecting various bus bars, and therefore, we will be dealing with Y bus matrices which can be as large as 1000 into 1000 or even more. Another characteristics that we see for this Y bus matrix is that it is a symmetric matrix. That is, what we are seeing here is y12 is equal to y21 is equal to minus y12, that is minus small y12. So, what we are saying y12 is equal to y21, y13 is equal to y31, y23 is equal to y32, that is, we are seeing that the matrix is a symmetric matrix. Another feature of this Y bus matrix is that Y bus matrix is a very sparse matrix, that is, almost 90 to 95% of the elements of the Y bus matrix are zeros, and very few elements which will be there are non-zeros. This comes mainly from the property that we have seen here, now. If we see here in this network, there is no line which is connecting bus 1 to bus 4 and bus 1 to bus 5. So, the y14 and y15 are 0, and therefore, we will have no element, non-zero element for these in the Y bus matrix. Similarly, in a very large network, we do not have all the bus bars connected to all other bus bars. So, if we are talking about a 1000 bus system, then in that case each bus bar may be connected to some 5 or 7 bus bars. So, what we see is that there will be only 8 entries in that row for that bus bar or in the column for that bus bar. So, rest of the other elements 992 elements will be zeros, and so will be the case with all the other bus bars also. So, we are finding that out of the 1000 elements, most of the rows and columns will be having only some 8-10 elements, and rest the elements will be zeros, and which shows that the number of zeros in the Y bus matrix will be very large, and therefore, these matrices are called sparse matrices, and we try to take advantage of the sparsity of this matrix in our computation process very much. In fact, sparsity is a property which is available or prevalent in all very large systems. So, Y bus is a sparse matrix. Diagonal elements of YII are obtained as algebraic sum of all elements incident to bus I. That is, we had seen that Y11 or Y12 is nothing but the algebraic sum of all the admittance which is connected to that bus. So, if you see here, Y11 will be equal to Y120 plus Y12 plus Y130 plus Y13, all the admittances which are directly connected to this bus bar. So, this is how we can calculate or find out the diagonal element of the Y bus. Of diagonal elements Yij is equal to Yji, because the matrix is symmetric, are obtained as negative of the admittance connecting bus I and j. That is, again, if we see this Y12 is nothing but negative of this Y12 that we have. In fact, these y's should have been small letters, whereas the Y bus matrix elements we have used capital Y. Okay, so these are some of the characteristics of Y bus matrix. Now, we will go in and see how we can derive the power flow equations. So, again we will go back to our basic equation. I bus is equal to Y bus into V bus, and if we take any particular bus injection, then I k will be equal to summation y k n into V n. That is, if we go back and see here, then I 2 is this. If we look at this, this is I 2 is equal to y, or let me see from here. Yeah, I 2 is equal to y 21 into V 1 plus y 22 into V 2 plus y 23 into V 3. So, it is summation of y I k is summation of y k n into V n. So, this is what we have written here. I k is equal to summation n is equal to 1 to capital N, where capital N is the number of bus bars in the system is. So, I k is equal to summation y k n into V n for n is equal to 1 to small n is equal to 1 to capital N. Now, we can write the complex power injection into bus k S k is equal to Pk plus j Qk, and this is equal to Vk into Ik conjugate. Now, Ik conjugate we can write from here will be conjugate of this. So, we can write Pk plus j Qk is equal to this Vk into this term is for Ik. So, Ik conjugate. So, conjugate of this term, where this can be written for all the bus bars, that is k can be from 1 to n. So, we can write this kind of a equation, that is the real and reactive power injection at any bus k can be written in this form. Now, we know Vn, or the voltage at bus n, is a phasor, and it is equal to Vn, the magnitude, into e to the power j delta I am sorry, this should be j delta n. J delta n. So, Vn is equal to Vn magnitude into e to the power j delta n. This k should not be here. E j delta n, and Ykn, the admittance, is equal to magnitude Ykn into e to the power j theta kn, where theta kn is the angle of the impedance. We have the impedance written as r plus jx, and the admittance will be 1 by r plus jx, which we can write as g minus jb. Therefore, we will have an angle depending on the magnitude of g and b for this admittance. So, we have Ykn is equal to Ykn magnitude into e to the power j theta kn. So, substituting the phasor Vn and for the admittance vector Ykn, we can write Pk plus j Qk, the real and reactive power injection at bus k, is equal to Vk, which is the phasor Vk, into summation Ykn into Vn e to the power j delta k is the angle for this, delta n is the angle for this minus delta n, because this part was our conjugate. So, conjugate means the magnitude remains same, the angle becomes negative. So, minus delta n into Ykn was here. So, Ykn we are writing with Ykn with an angle minus theta kn, because we this term is, this whole term is conjugate we have to take. So, these angles theta n and theta kn are negative. So, this is what we get from here, and if we now separate out the real and reactive part from this equation, then we can write Pk is equal to Vk summation n is equal to 1 to capital N Ykn Vn cos of delta k minus delta n minus theta kn. I am sorry, here this k is missing in this, and Qk is equal to Vk summation from n small n is equal to 1 to capital N Ykn Vn sin delta k minus delta n minus theta kn. So, we have the real and reactive power separated, and we can write the relationship between the real power and the reactive power in terms of the voltage magnitude and the angles at different bus bars and the admittance which is connecting the various bus bars in the system. That is real and reactive power equations are given like this. These equations are relating the real power and the reactive power with voltages at various bus bars Vk, Vn, where n is changing for all the bus bars, and Ykn where Ykn is the admittance which is connecting the bus k to all the other bus bars. So, let us see what is the characteristics of these power flow equations. Some of the important characteristics are that these power flow equations are algebraic equations. That is, if we see these equations are algebraic equations because there is no derivatives involved here or differentials involved here. So, these are just algebraic equations because we are using a static system condition. So, there is no differential equations involved, it is only an algebraic equation. Now, power flow equations are also, we see they are non-linear. That is, we have, if we look here, sine and cos terms involved here. Also, we have multiplication of v terms and so on. Therefore, these are non-linear algebraic equations. Since these equations are non-linear, the general procedure for solving these equations will be an iterative solution procedure. So, these power flow equations relate the PQ injections at any bus bar in terms of V and delta, the voltage magnitude and angle at various bus bars, and the Y bus elements. That is, PQ are a function of V and delta. Now, we will see exactly what is this power flow problem and how we try to solve them. First thing that we have to do is we will have to see what are the different variables which we have. Now, we see that in a power network we have at certain buses loads. Now, these loads are controlled only by consumers and the power system has no control on them. Therefore, these variables are called uncontrolled variables or disturbance variables, whereas generation PG and QG are controlled by the power system operator. Depending on the load on the system, he raises or lowers the generation at different generators. As we will see later, he also tries to optimize the cost, that is, for a given loading condition he tries to find out what should be generation at various bus generating stations, so that the total cost of operation is minimum. That we call as economic dispatch problem. So, he adjusts this generation at various bus bar so that he gets an optimal performance, and therefore, these variables, generation variables PG, QG are our control variables, whereas the voltage magnitude and angle at all the bus bars, which basically relates these control variables as well as disturbance variables in the system, is the state variable of the system. In fact, if we know these values of V and delta at all the bus bars in the system, we can find out all the other values, and therefore, we call this V and delta, that is voltage magnitude and angle at bus bars, as the state variables. Now, what is the power system problem, power flow problem? The power flow problem is for a given operating condition, that is loads and generation at all the buses, we have to find out the voltage magnitude and angle at each bus. That is, given the disturbance variables and the control variables, that is, if these are specified, find out what is the state variable. That is, for any given operating condition, any particular time when we have this all the loads and generation known, then we can what we need is, we need to find out for these generation and load what is the voltage at various bus bars, and once we know this, then we can calculate all the line flows and all the other variables. Now, what is the problem in formulating or solving this equation? Well, one of the problem that we face when trying to formulate this power flow problem is that all generation variables Pg and Qg at all the bus bars cannot be specified. Why we cannot specify the generation at all the bus bars? The loads are known. We can say that we can give the generation also to satisfy this load. Unfortunately, this is not possible because the losses in the transmission line are not known. They will be known only after we know what are the flows in the transmission lines, and so we know the current flowing in each line, and we can find out the loss taking place in each line. So, unless we know the voltages at all the bus bars, we cannot find out the current flowing in various lines, and therefore, we do not know the losses. So, if we do not know the losses, then we cannot specify all the generation, because the total generation must be equal to the total load plus the transmission losses. So, how do we solve this problem? Well, in power flow problem, what we do is we say that one of the bus bars, normally a large generating bus bar, we do not specify its generation. We say that this bus bar is going to take or absorb all the transmission line losses. So, we specify the generation at all the other generators or generating bus bars except for this one bus bar, and since this bus bar takes the slack, that is the losses in the system, therefore, we call this bus bar as a slack bus bar, and we have one slack bus bar in one system. So, what we do is basically we are choosing a reference bus, that is one bus where we are not specifying the real and reactive power generation. Now, if we do not specify real and reactive power generation at this particular bus bar, then we have to specify some other two variables at this bus bar, and normally the variables that we specify at this bus bar will be the other two, that is the voltage magnitude and its angle. Since the angle have to be specified, we normally will choose an angle equal to 0, and therefore, the voltage angle at all other bus bars will be related to this bus bar's angle. So, this bus bar can be seen as a reference bus bar where both voltage magnitude and angle are known or specified. So, we see that we have different kinds of bus bars in the system. One, we have just now seen we have to specify a slack bus, that is a bus which can take care of the transmission losses. So, we can say that each bus K is classified into one of the following three bus types. One, the swing bus bar or the slack bus bar. This is only one swing, there is only one swing bus which is for convenience numbered bus 1. We can number it, it can be any bus as such, but we will generally use bus 1 as the swing bus. The swing bus is a reference bus for which V1 and delta 1, which we typically 1.0 angles 0 per unit is specified, that is the input data. The power flow program computes P1 and Q1 for this bus, that is the unknown for this bus will be P1 and Q1, that is injections at this bus, because we have not specified the generation at this bus. So, we need to calculate that finally after we have calculated the voltage at all the bus bars. Then other type of bus bar is a load bus bar, where both real and reactive power are specified. At this bus bar, what are the unknowns? If we know V and delta at this bus bar, we have all the variables. So, here P and Q are specified, that is injection, real and reactive power injection is specified, and the unknowns at this bus bar are V and delta, voltage magnitude and its phase angle. We have a third type of bus bar, which we call as voltage control bus bars. These are generally bus bars where we have generation. At these bus bars, Pk and Vk are specified, that is the real power and the voltage magnitude is specified, and the power flow program or the solution of power flow will provide us the reactive power and the voltage phase angle. Now, these bus bars, as I said, are generally the generator bus bars or switch shunt capacitors or static var systems. So, bus bars which have these, they are generally PV bus or voltage control bus. The main reason for this is, at these bus bars, since we have reactive power control available, so we try to keep the voltage controlled or the voltage magnitude at some specified value, and therefore, the voltage magnitude can be specified, and since these are also generator bus bars or maybe load bus bars, the real power at these bus bars are known. So, once we have fixed this magnitude of voltage, once we calculate the delta angle for this voltage, then we can calculate Q for this voltage. So, Q and delta are the unknowns for this. Sometimes maximum and minimum var limits, that is Pgk max and Pgk min for the equipment is also specified, and in case we find after the solution that the value of the reactive power, that is Qk, is exceeding these limits, then we fix the value of Qk to these limits and consider these bus bars as load bus bars, because both P and Q are now fixed at these bus bars and V and delta need to be found out. Okay, so, with this we come to the end of today's lesson. We will talk about the solution methods for power flow equation in the next lesson. Thank you very much.